So now we will cover a lot of problems for the Karnaugh map, a lot of SOP expression, a lot of POS expressions, and then see we will do a lot of examples here. Okay. So we covered with this thing. Can you look at here now? If you look at this problem, how many squares do we have here? How many squares? 1, 2, 3, and 4. We have one square of 4, 3 squares of 2. If you look at here, so now we have AB. Now we are going from where? We are going from column 1 to column 1 to column 2. Column 2 to column 3. Yes, we are going from column 2 to column 3. What is changing? A is changing. What's the value of B? 1. When B is 1, B. Now we are going from row 2 to row 3. When we are going from row 2 to row 3, what's happening? So C is changing, and now D. Can you see D? Now the value of D is 1. Okay, now can you see here now the yellow part? In the yellow part, if you look at the yellow part, so now A and B are not changing. What's the value of A? 1. In this column, in the last column, the value of A is 1. So now look at here, the value of A is 1 and B is 0. So this is AB bar. But now if you are going from row 1 to row 4, what's changing? D is changing. The value of D is 0. So this is actually C is changing. Okay, so now D, what about D? It's D bar. Again, if you look at the third, this square of 2, this square of 2, please look at here. The square of 2 will give us how many literals? 3 literals. A square of 4, 2 literals. Okay, and a square of 8, 1 literal. So if we have increasing the square size, it will reduce the, so going from 2 to 4 will reduce the number of literals by 1. From 4 to 8, it will further reduce the number of literals from 1. Got it? So now this is how it works. So now if you look at for this green thingy, for the, now we are in column number 2. In column number 2, can you see in the column number 2, the value of A is 0 and the value of B is 1. So this is A bar B. And now we are going from row 1 to row 3. What is changing? D is changing. The value of C is 0. So this is C bar. A bar B, C bar. Got it? What about this? What about this? Now only one is left. This one. Please give me this expression. Anyway, which one? A bar B bar. Can you see? A bar B bar, because both are A bar B bar here. A bar B bar and then C. A bar B bar C. This is how it works in the Karnaugh map. So now this is the final expression. So the final expression consists of 4 product term. It consists of 4 product term. So it means that now this is a final expression consists of 4 product term. The first product term consists of 2 literals, which is derived from a square of 4. The second product term consists of 3 literals, which is derived from a square of 2. Similarly, the third and the fourth product term, the third and the fourth product term, all of them are what? Min terms or prime implicant or implicants? All of them are implicants. All of them are implicants. Okay, and each implicant, but not all implicants are prime implicants. Okay, so all of them are implicant. So now we can say now we have a K-map. Now we have a function of 4 variables. Okay, now look at here. Now whenever we want to solve this problem, then we are interested in the larger group. Where is the larger group? Can you see where is the larger group? So now this is a larger group. Now we first need to cover the larger group. Can you see here? We need to first cover the larger group. So now this is the expression. So now what is this? It is a sigma of 0 to 589. Okay, now if you look at here, this is the sum of the min-term form. It is the sum of the min-term form. And how many ones are there? 11 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 ones. There are 11 ones. Okay, now if you look at here, so now it is 0, 1, 3, 2. Why? We are going in the downward direction. Because AB is here. If AB would have been here, so now this is 0, 1, 3, 2. 0, 1, 3, 2. 1 is not there. and 0 and 2 are here. So if you look at the color, this is 0, 1, 3, 2. 1 is not here. Then 4, 4 is not there. 5, 7, 6. Then 12, 12, 13. 12, 13 is not here. Yes, please. 3 is not here. Maybe they did it with the horizontal line. Maybe they did it with the horizontal line. But still, if you look at here, so now this is, maybe this is some mistake. Can you see? Yeah, this is a horizontal one. Can you see here 0? If you look at this big circle, how many ones? 8. Okay, now how many ones? 8 literals. As 8 ones. It's a big circle. So we start with the big circle. How many literals can we get? One. Only one literal. In one literal, and what is that literal? A. Can you see? A is same. A. Okay. Now please look at what should we do now? Now we should go for another. Which one? All corners. All corner. This, and this. All corner. All corners. And then how many literals should we get? 2. We should get 2 literals. So if we're going from A, what is changing? B bar and then D bar. B bar, D bar. And what about now we have, what is the other group that we can use? These 2. How many literals? 3 literals. So now there are 3 literals. So now if you look at the function, now this reduced function consists of 3 implicants. Okay, so now this A is a result of an implicant with 8 square. It is a result of an implicant with 4 square, and it is a result, the third term is an implicant of 2 squares. Okay, because of 3. Now we have expression. Okay, now if you look at the standard SOP expression, in the standard SOP expression, or the standard sum of the minterm expression, how many ones are there? 11. There are 11 ones. 11 ones. Now this is a function. This is a function of 4 variables. So now if we have 11 sum of the minterm expression, so each minterm will have 4 literals. We have 11 ones, and each minterm has 4 literals. So how many literals can we have in the unreduced expression? 44. 11 ones multiplied by 4. Why 4? Because each minterm consists of 4 variables. Now each literal consists of 4 variables. That's the reason that now we have reduced this expression from 44 literal, which is actually the standard sum of the minterm expression, and now we have reduced to how many literals? 6 literals. Any question? Got it? So now what is the strategy? So what the strategy is for circling the rectangle on CAM map? We call this as prime implicant. We could go for the bigger one, and when we go for the bigger one, we should not divide the bigger one into many small groups, because if you look at the bigger one is shown in blue color. So we can also here, this is another implicant here, this is another implicant here. So when we go for the bigger one, we do not further subdivide it. Okay, now the thing is, all of the ones that belongs to the bigger one can be shared with other, but the same bigger one cannot be further subdivided into further implicants. Got it? So a group of this 11 cannot be further subdivided into some prime implicant. That's the reason that it is called as what? The prime implicant. Any question? Should we proceed? Okay, so now it should be as big as possible, and then we wrap around. The wrap, where we are using the wrap around? Corners. Which color? Red color. So now we also wrap around. So now if you look at here, so now this is a very tricky question, because by definition, if you look at here, by definition, these are a group of 2, and a group of 2, and if you look at the middle one, this becomes redundant. This becomes by definition. So by definition, please also look at here, because this one is scored by 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 this one, and by definition, a group of 4 is actually a redundant one. But But for the sake of thing, we can take this. Got it? So now, if you look at here, now we are simplifying a two variable. So find the simplified expression for G, A, B, C, D, and then look at how can you make a simplified expression. Yes, please.
We should take the bigger simplifier.
Yes, we should take the bigger one, but this is a when. But please have an expression. So if I take this one, I take this one, I take this one, and I take this one, all these four. So now in the bigger there is a problem. I will solve it. I will solve it. Okay. So now what I'm doing it, because this is a little tricky question. This is a little tricky question. This is a little tricky question, and now I am enabling it. I'm turning on the camera and stop sharing. Share video. Is it visible? The video is visible? Yes or not? No. Where we are now? The door. Oh. Oh. Uh-huh. Now, because I want to zoom on this one. Okay. Good or not? Okay, then. But see the problem. First we solve the problem and then I can say here. Okay, now, and this is a very tricky problem. This is a very tricky problem. What is the value of A, C, D? 0, 0, 0, 1, 1, 1, and 1, 0. This is A, B. Is 0, 0, 0, 1, 1, 1, and 1, 0. Where are the ones? 1, 1, 1, 1, 1, 1, 1, and 1. Okay. Now I'm using different colors, and to understand, to have the concept. Okay. Now these are two ones, and this red one is a prime implicant because this one cannot be shared with any other one. Got it? Now look at this one. Why this is a prime implicant? Because it cannot be shared with any other one. There is no any other thing that we can share. Now we have this green one, which cannot be shared with any other prime implicant. Now which one do we have? All of them are covered. Now if you look at this expression, and all of them are covered. But if you look at this expression, what is the expression for F? Help me, help me. Now red one. I'm using the red color. Red one, yes please. A bar, B, C bar. The red one. A bar, B, C bar. Got it? Now we have another, the black one. The black one. What is the expression for black one? A, C bar, D. Now we go for the blue one. Help me. A bar, C D. A bar, yeah, C D. Okay, now the green one. Which one? A B, and then C. Now if you look at here, okay, now the thing is, we always go for the larger group, but here this does not apply, because if you go for the larger group, so then it becomes redundant, and then we need to exclude the redundant one. Okay, assume that now the thing is, so if you look at here, so all ones are covered. All ones are covered. Yes, all ones are covered. But the thing is, if we take this, assume that we take a big square. We take a big square. If we take big square, what will be the expression? Yes, just for the sake of example, we take this big square. This big square. So now we have B and then D. Is it redundant or not? This is redundant. You should go for the big squares only if it is not redundant. Because the thing is, and now this big one, can you see here the square of 4? So this square of 4 in the middle, the square of 4 in the middle, I'm not drawing it because you know it is, the square of 4 in the middle is not an essential prime implicant, because it has this one which is shared with the red one, which has this one which is shared with the black one, and which has this one which is shared with the green one, and this one is this one which is shared with the blue one. So that's the main philosophy. That's the main philosophy, that why we need. Okay, now we have, if for the first instance, if I give you this tricky question, oh, I didn't give this in my midterm exam, but if I give you this tricky question in exam, everyone will start with the big one. But that is now redundant. So be cautious. Be cautious. So whenever you are solving any question, you should try for the big one, yes, but you should take care of that this should not be a redundant. Any question? Should we proceed? So this is a very classical example. This is a very classical example. Okay, now I switch back to my presentation in the presentation side, and then I can share screen. Share application screen, entire screen, this screen 1, share. Now, if you look at here, so now we have now we are simplifying a 2-variable function, and a 2-variable function. Can you see here what are the name of the variables in this particular example? X and Y. So now we have f is equal to m0 plus m2 plus n3. 0 0 m0, 1 0 m2, 1 1 m3. m0 plus m2. So this is one is m0, one is m2, and one is m3. This is m0. This is what? m2, and this one is m3. So now 3. So in the standard form, so it's a function of 2 variable. Every minterm consists of 2 literals, and in the sum of the sum in standard form, so we have 3 minterm. Each minterm has 2 variable. So it is the unreduced expression which consists of 6 literals. But if we solve this, so we say m0 plus m2. Can you see m0 plus m2? m0 0 0 0 x bar y bar. I'm not looking at it. m2, what is m2? 1 0 x y bar. We now do the algebraic manipulation. When we do the algebraic manipulation, it is equal to y bar. When it's equal to y bar, and then we see the red one, so x is changing, y is not changing, its value is 0. That's the reason it's y bar. So now this is also, so if you want to solve a problem in any exam, so you can do both algebraic manipulation and the Carnap map to verify that your answer is correct. Got it? What is x bar plus x? 1. So now can you see here? So now if you look at here, now this red one is actually consist of 2 minterms, the minterm 1 and minterm 2. This is m0 and this is m2, and then we transform this into. Now we look at other. Can you see these two? We can also see. So what is these two? m2 plus m3. Okay, so now we want to we have now solved m2 plus m0 plus m2. Now we look like to have m2 plus m3, which is actually the blue one. In the blue one, m2, without looking into this, m2 1 0 1 0 1 0 xy bar. I'm not looking at it. m3 1 1 xy. Take what's the common? X, y bar plus y 1. With 1 bar plus 1 plus 1. So now this is the algebraic manipulation. So now if you look at solve it using Carnap map, we get x plus y bar. And if you use the algebraic manipulation, so algebraic manipulation, we also did algebraic manipulation. We also get the same expression. So this consists of 2 literals. So we have reduced from 6 literals to 2 literals, because in the unreduced expression we have 3 minterm. Each minterm consists of 2 literals. So we have 3 ones, 3 multiplied by 2, 6 literals. So we have reduced from 6 literals to 2 literals. Any question? Should we proceed? Okay, now we have another 3 variable, and now we will do a lot of examples. Why I'm doing this example? Why did I give you complicated question in the midterm? Because the reason is I will ask these kind of questions in your second midterm or second upcoming quizzes. That's the reason that I make it a little bit simple. We didn't cover it. So now if you look at consider this function, so now this function consists of how many minterms? How many minterms? 6. How many expression in the unreduced form? 18. 6 multiplied by 3 is 18 without looking into the thing. So I may also ask this question, or if you want to calculate, okay, how many literally you will calculate, you can directly use it from this function. So now we have a variable of 3, function of 3 variable. When we have function of 3 variable, it has 6 minterms. Each minterm consists of 3 variables. 6 multiplied by 3, unreduced with 18 literals. Okay, now we have transformed this into the Carnot map representation. So now we have how many ones? 5 ones, and we fill this. We have 5 ones. Now we look for the solution. Okay, now we can have a group of 4. This is a bigger group. So we a group of 4. So now what term is this? Z bar. Why Z bar? Z is not changing. Y is changing and X is changing. X is changing. Can you see? If you can think of this, it covers both X bar and X. So X bar plus X is 1. And then what is changing? So if you look at here, Y is also changing. So this is Y bar plus Y. And if you look at the red one, so this red one consists of how many minterms? 4. So can you look at here? So this is consists of 4 minterms. So we can express this. This is the now this one, X bar, Y bar. So Y, this is X bar, Y bar. So now this is XY. So now this, the final expression is Z bar plus X bar, Y bar plus XY. Got it? Okay, now the red one, this red one, which ones does it covers? Yes, please. The red one, 0, 0, 0, 0, 0, 0, 1, no, 1, 0, 0, 4, then 0, 1, 0, 2, there's 1, 1, 1, 0, 6. So this term, the red term is what? M0 plus M4 plus what? M2 plus M6, and then you can do the algebraic manipulation. So if you add this minterm, this minterm, this minterm, this minterm, this should give us Z bar. Second thing. Now if you look at the blue one, so this is 1, this is 1, 1, this is M7, this is 1 and 1, 0, M6. So M6 plus M7, if you go through M6 and M7, it will give you X bar. And the same thing, the same is for the last one. So you go through all these things. Any question? Should we proceed? Okay, now we have another function, a function of 3 variable. It consists of 4 minterm. Each minterm consists of 4 times, so 4 minterms. Function of 3, 4 multiplied by 3, 12. We mark 1, 5 all the possible adjacent. This, can you see here now? This Y, again, we also do the algebraic manipulation here. This is what? X bar YZ, X bar YZ. This is actually, can you, the first one, X bar YZ, and then the second term, XYZ. So XYZ, and we do the algebraic manipulation, so we also get it. YZ. Again, this red term, it consists of how many minterms? 2 minterms, and we do it using, so now this one is the algebraic manipulation, and this one is Carnot map. We reduce to 4 letters. Got it? So this one, the first one is the sum of the minterm expression. So this is the sum of the minterm expression. This F is the sum of the minterm expression. This sigma is the sum of the minterm form. This is the sum of the minterm form. This one is the sum of the minterm expression. And if this F is actually the reduced sum of the product expression. This is called as a sum of the product expression. We do not have a sum of the product form because we don't know, because it covers a lot of minterm. So we have the last one is the sum of the product form. It is the reduced, the minimum possible reduced sum of the product form. So now these are the definitions. So so if I ask some questions, so please remember. What is the first? What is this thing? Yes. Sum of the minterm form. What is this? Sum of the minterm expression. What is this? The reduced sum of the product expression. We do not have the reduced sum of the product form. Remember this thing. So this is unreduced SOP expression. This is the reduced SOP expression. We can also call this is the reduced sum of product. Yes, it is also the unreduced sum of the minterm expression. We can also call it this unreduced sum of the product. Both things are there. Okay. Now we have a 3 variable function, and we have another example, the same thing. So learn the location. Again, something corner squares can be combined. We can also combine corner square. Okay. Now if you look at the red thingy, the red circle, are we solving it using which method? Carnap map. This is the map, and this one Boolean expression. So now you are combining these two, and now we have reduced to this. Now consider this Boolean function f. The 4 minterms that form the red square are reduced to the term y. The 2 minterms that are the blue rectangle are reduced to the term xc. And this is called as x plus y plus xc. Any question? And can you see the red one? The red one consists of how many minterms? The red one, 4 minterms. This is minterm 1, minterm 2, minterm 3, and minterm 4. And then we do the algebraic manipulation, blah blah blah. So this one is easy. Carnap map is easy, or this one is easy? Carnap map is much better. So that's the reason that a lot of people say, oh, algebraic manipulation is easy. Algebraic manipulation is not that easy, because if you involved in algebraic manipulation, it will do a lot of steps. And then this is algebraic manipulation. Now getting POS expression. How can we get the POS expression? There are 2 methods. I will also explain method number 1 on the board and method number 2 on the board. Okay, because sometimes you want both methods or one method. Yes, please. If you're confused with the second method, I will not do it. Both methods. Okay, let's go with the first method. So now please look at here. Now we want to get which expression? POS expression, not the SOP expression. We want to get the POS expression. Okay, in POS we are interested in 1 or 0? Zeros. But what we can do, we can say, so now what is this? M4, M12, M13, M15, M14, and M6. Why I have highlighted this in red? Because these are all zeros. But the problem here is now this. So now these are what? These are the minterm forms, but we want to have it in the maximum form. So what we do, so the zeros are then converted. So now this is f. If you want to get f bar, so now this is a function f, and this is f bar, because now 1 will become what? Zeros, and 0 will become 1. So now this is the function f, and now this is the function f bar. Got it? And then we solve it for f. So if you look at here on the left hand side, we have f function f, and now we have the function f bar. If you look at the function f, now this is the function f. How many ones are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 ones. If there are 10 ones, how many zeros? 6 zeros. 10 plus 6 is 16, because 2 to the power 4 is equal to 16. So 2 to the power 4 is 16. So we have 10 ones and 6 zeros. But if we have 10 1 and 6 zeros in f, then we have 10 zeros and 6 1 in f bar. So that's the reason. So now we have 1-to-1 correspondence between f and f bar. So now if we say, now this is the function f in its original form, and to get the POS expression, the product of the sum expression, we complement the function. So now 0 will become 1. 0 will become 1. So now this is the K-map of what? F, and this is the K-map of f bar. Why we are interested in the K-map of f bar? Because we want to get the POS expression. This is method number 1 or method number 2? Method number 1. I will also go do the method number 2, and that's the thing. So now if you look at this, so this gives out the SOP of, now we are getting the SOP of f bar or f bar. We are not interested in the SOP. So now if you look at the f bar, so now we have, can you see here the whole, and now we also have these two. Got it? Okay, now if you look at the, can you see this expression? If we cover all these ones, what will give us? The third column. AB. And now we have, can you see? Now this is a big group. Consists of row 4 and row 1. So what's changing from here to here? What's changing? D bar, and then B D bar. B D bar. Got it? So now we have this thing. This is AB, and now can you see? We have two big groups. Instead of small group, we have two. Got it? How do we get it? Can you see the color coding? Because I tried a lot of effort in in this color coding. So now if you look at the blue one, so the blue one consists of 4 ones, and the other one, the shaded one, the green one, also consists of 4 ones. And now it will have a reduced SOP expression for F or F bar. F bar. Now we get this to get the pause. To get the pause. So can you see here? So now we have this F bar, and then I can then turn on the camera and stop sharing, and then turn out the camera, and then I can explain it there. You got it? We got what? We got F bar. What is F bar? BD bar plus AB. But we are not interested in F bar. We are interested in F, because we want to get the pause expression. So if we are interested in F, so we need to complement both. So now we say F bar whole bar is equal to BD bar plus AB what? Whole bar. F double bar is what? F. So now De Morgan theorem, B D bar whole bar dot AB whole bar. This is what? D double bar dot A bar B bar, and this is what? So this is what to get the pause expression. So now we do this De Morgan theorem, we do this, and do this, and then. Got it? But now it's important. Please look at here, and this is very important. Now in the first approach, what we did in the first approach, we get the SOP expression. We get the SOP expression for what? F bar. But we can also get it directly from here. How can we get it directly from here? Can you see here? Now, please, can you see the color coding? Can you see the color coding? Which color is this? Black. Look at the black color. So now, if you look at the black color, so now in the black color, now A is not changing and B is not changing, and now we have a 0. And in the pause expression, we complement it. So can you see here? This is what? 1 and 1. So this what we get? A bar plus B bar. And now if you look at here, so now this is, so we take 1 in true form or complemented form? 1 is complemented form for the pause expression. 1 is if you want to directly take 0 directly without converting into SOP expression. So now if you look at here, so now in the third column, what is the value of A? 1. What is the value of B? 1. So how can we get the SOP expression? A plus B. So this is A plus B. No, 1 and 1, A bar plus B bar. And now if you look at here, so now we have, what is the value of B? 1. That's the reason we got B bar. And what is the value of D? 0. That's the reason we got D. So this is, you can do it directly. You can do it directly by considering the 0 and combining all zeros, make some group, and if it is 0, directly write it in true form. If it's 1, then write it in complemented form for the pause expression. We know the rules that how do we calculate the SOP expression of the pause expression. Any question? Should we proceed? That's up to you, whatever. So if I say this question, if I ask this question, derive the SOP expression. It's up to you. It's up to you the choice. So maybe I give you maybe it's also possible I give you the sigma form, that this is the sigma form, and derive the SOP expression for this sigma form. So then you convert it into pi function. When you convert it into pi function, then put you 0 all this pi function, and then you can solve it directly. So there can be a lot of methods that you can do. Got it? And we also know that how can we convert from the sum of the product form to the product of some form. Yes, please. Yeah. So these are all the rules that we defined before. Remember, we also did it. How can we convert u from sigma to pi? Remember? So if there is a sigma, so we can also convert it into pi. So if you remember, if we have assume we have a function of two variables. Assume a function of two variables. Sigma fab, sigma of 1 2. How can we convert it into fab is pi of what? 0 3. Remember these rules. So now fab, what are the possible values? 0 1 2 3. How can we convert it into pi? Because just come, and then you can get the f bar and dot. So now can you see here? Okay, ab. What are the possible values of ab? Yes, please. What are possible values? 0 0 0 1 1 0 1 1. This is what? 0 1 2 and 3. Now this is f. F when it is 1 1 and 2 1 and 2. So this is 0 and this is 0. So now we write this f in the sigma form. So sigma form is what? 1 and 2, and pi form is what? 0 and 3. So this is the pi form. So you can convert. So I may give you in the sigma form and ask you for the pos expression. I may give you in the sigma form and ask for SOP expression. I may give you the pi form and ask for SOP expression, and I may give you the pi form and ask for SOP expression. So all of the possible combinations are there. So please think that how can you, and now this is a function of how many variables? 2. I may give you a function of 3 variables. I may give you a function of 4 variables. Got it? That's how. I will not give you a function of 5 variable. 5 variable is a little bit more complex, but still you need to know the concept. So you need to know that how can you convert from f to pi. Okay, now please think. Now if you say f bar, what is f bar? Can you see here f bar? Now this is f bar. What will be f bar? 1 0 0 1. Again, I'm repeating the old topics. All I'm repeating the old topics. Now what is f bar ab in sigma form? Sigma form 0 3. No, 4 is not there. 0 and 3. And f bar in sigma form 1 and. So please, you know, you need to. So you can convert from this to this form. You can convert from this to this form, and you know these rules. You know this formula. That how do you do it? Okay. So now you can convert from one form to other form. So in the exam I may give you the sigma form and derive the SOP expression. I may give you the pi form, derive the SOP expression. Then I can give you otherwise. Got it? So we proceed further, and now it's a don't care condition. It's a very important concept. So in certain problem, some output are not specified. These outputs can either be 1 or 0. These are called as the don't care condition, denoted by X. How I explain this? I can explain this with an example. Okay. Please raise your hand. Okay. Okay. When you raise your hand, I give you attention to you. Oh, what's your question? So did I ignore you or did I answer you? Answer. Okay. Now, if you raise your question, you raise your hand, and then I'm ignoring you. This is called as a don't care condition. Either you raise your hand or you put your hand down. I'm ignoring you. This is called as a don't care. Don't care. I don't care. Just like in this thing. So what is the don't care condition? So now assume that we are using with some digital codes, BCD codes, BCD codes. So now we have any digits. What is the valid value of any BCD from 0 to where? 9. These are valid code or invalid code? Valid code. But if from 10 to 15, invalid code. These are called as the don't care condition for BCD. Will all these entries be don't care for hexadecimal? No. So this will not be a don't care for hexadecimal, but it's a don't care for BCD. Why in BCD? Why in BCD? Because BCD range from 0 to 9. This is called as the don't care condition. So we assume for BCD, we assume that the input, the valid range of the input for any BCD digit is from 0 to 9. So these are called as the valid code, and the valid code are shown in this blue color, and these are called as the valid BCD code, and these are invalid BCD code. Why we are? So it means that for these combinations, the red one, these are don't care. And that's the reason that I asked one question in the exam about BCD that you should know, because I would teach it what is a BCD. If you don't know BCD, then there is a problem. So now output is don't care for invalid BCD code is don't care. Okay, don't care condition can be used to help simplify the Boolean expression further in CAMAP. They could be chosen to be either 1 or 0 depending on which gives the simpler expression. I'll explain this with an example. Can you see here? These are all ones. 1, 1, 1, 1, 1. How many ones are there? 5. And then we put 6 don't care condition. Why we put 6 don't care condition here? Because these are invalid BCD. Assume that we want to solve some expression for BCD, so we also include these don't care. Okay, so in this case, all of these ones are separate ones. They cannot be grouped with anything. This is a separate one. Yes, this is a separate one. This is a separate one. This is a separate one. Can you see here? What's A bar, B bar, C bar, D bar, A bar, B, blah blah blah. How many terms we have? 5. Term 1, term 2, term 3, term 4, and term 5, because there are 5 ones, and they cannot be grouped with anyone. Assume that we want to calculate the parity. We want to calculate the parity for the BCD code. Calculate the parity for BCD code. These are the basic. So now we want to calculate the parity for BCD code. We want to calculate it here. Now this is from here. It cannot be grouped. Can this group 1 be grouped with any other group 1? No. Can it be grouped? Can it be grouped? Can it be grouped? No, not possible. But since it is a BCD code and we want to generate a parity for this, so we don't care. So now we can combine it. Now what we can combine? Oh, it cannot be used, combined with any other. This can be combined with this don't care. Now we have a bigger group. We have a bigger group. When we have a bigger group, this is B bar CD. What about this? BC bar D, BCD bar. So if you go through all these examples, so what is the advantage of don't care? It helps you in logic minimization. This don't care can be combined. These don't care can be combined with ones to further simplify your logic expression. So in the first expression, we did not consider the don't care. It gave me a bigger expression. But in the second case, we combine these don't care condition with the ones, with the particular one, with the same example. Now, okay, now if you look at here, the first expression consists of how many literals? Literals 20. And in the second case, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So now the expression has been reduced by 5 literals. Why? Because of the don't care condition. Because can you see here? Now we are using, it will reduce by 1 literal. This group will reduce by 1 literal. This group will reduce it by 1 literal. 2 literals. This group will reduce by 1 literal. 3 literals. And the square of 4 will reduce by 2 literals. 1 plus 1 plus 1 plus 2. How many literals have we reduced? 5. And that's the thing. And why we were able to achieve this? Why? Because we included the don't care condition and combined it with the possible ones to make a larger group. And when we make a larger group, it helps us to reduce expression. Yes, please. So that's the thing. This is very simple. So if you look at the above, what are the invalid BCD code? 10, 11, 12, 13, 14. Got it? So now 10, 11, 12, 13, 14, and 15. And you remember, I already combined it. 1010, 1011, 1100, 1101, 1110, 1111. How many combination? 6 combination. So can you see here? 1111. Where is 1111? 1111. This is not here. Got it? Or not got it? Yes. 1111. This X. Which one? 1110. 11. No, AB. 11. And then 10, this X. Got it? So now what we do, so now we say, so now if you look at the Karnaugh map, we have 16 possible combinations. What are the 16 possible combinations? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What are the invalid combinations? 10, 11, 12, 13, 14, and 15. So all of these X, this one is 1111, 1111. It belongs to what? 15. Got it? Any question? Should we proceed? Yes, please.
So for some care as one.
No, they don't care. We say it can be treated either as a logical 1 or a logical 0.
In the K-map, we treat them as one. So we
We treat it as 1. We treat it as a combined 1. We don't care. Either the value is 1 or 0, we don't care. Either the value, okay, now it can be 1, it can be 0. Actually, the value can be 1, but since it is not possible that this value will occur, so we treat this as 1. And it will further reduce the logic expression. Any question? Should we proceed? Okay. Now, the reduced logic expression, we don't care. Now, the K-map techniques. Okay, now I will also now have a summary of all the techniques that we did. So, we use some algebraic simplification. Algebraic simplification requires skills but extremely open-ended. I also give some questions to the students, and a lot of students face a lot of problem with this algebraic manipulation because you need to know a lot of laws. But solving these techniques using K-map is easy or difficult? Easy. Carnot map can obtain simplified standard form. We can have two different standard form. What are these standard form? SOP expression or POS expression. We can have reduced SOP expression or reduced POS expression. Now it is easy for human because pattern matching. You can identify per pattern. You can have a pattern of 2, a pattern of 4, pattern of 8, pattern of 16, and blah blah blah. It depends on the number of literals or the number of variables. But it is limited not more than 6 variables. So there are also some other techniques. We don't do it, but it's not like that. So now this is a 2 variable Carnot map, 2 variable Carnot map AB. This is a 3 variable Carnot map. Can you see here? This is M0, M1, M3, M2, M4. And referring to your question, can you see here? We have this don't care condition. What is this? M9, no, 10, 11, 14, 15, and 12, and 13. All of these are what? Got it? Can you see a WXYZ? So what's what don't care? So don't care are this 10, 11, 12, 13, 14, and 15. And you look at all the previous answers. Can you see? 1, 10, 6. Got it? Yes. Now. So now 3 variable Carnot map ABC is a 4 variable Carnot map WXYZ. Grouping, now we can use, it should be rectangular in shape. It should not be a diagonal value. It should also be on the power of 2. Always select the largest possible grouping of min term, but you should only consider which implicant? Prime implicant. It should have at least one that is not covered by the. You should select the best big one, but if that big one is redundant, you exclude it because we did it in that example. You exclude it. So we can give the sum of the product expression by selecting group of min term corresponding to product term. And then we can also derive the product of some expression by selecting group of max term, not a min term, by selecting a group of max term. If it's a group of max term, are we interested in 0 or 1? Zeros. And corresponding to some term by applying De Morgan theorem, you can also apply. You can have F, then you give the F bar, and then you apply the De Morgan theorem. And if you have don't cares, it can be marked by X or D. It means that we don't care. And it can be used to simplify the expression. So now this is example number 1. Fill in the ones. Can you see here? These are what? All prime implicant. Do we need them all? Which are redundant? No, not the blue one. The pink one. Now, can you see the pink one is also redundant? This one is also redundant because this is covered by, so this one is covered by pink one and also the blue one. And this one is covered by this one and this one. So this is all redundant. So yes, all they are redundant. Remove all the redundant. And then there are some left. When there are some, these two are left. These are left. The thing is, it's very complicated. It's a little bit tricky. Can you see this one is shared by the blue one and the pink one, and this one is shared by this blue one and this blue one. So this is also redundant, and this is also redundant. Why this is redundant? Because it has a one which is shared by what? The pink one, and it has a one which is shared by the shaded one. So we remove this thing. But when we consider the prime implicant, why this is a redundant one? Why? Because this one is shared by what? This side. Okay, and then it's also shared with this one. That's the reason. And this one is shared by this one is also redundant. So then, what is the expression for this? What is the expression for this? What is the expression for this? But one is left. So we need to include the one. This is called the essential prime implicant, but then it's called as the minimum cover. So whatever is left, after extension, then you need to cover it. You cannot ignore it. You must cover it. This cover is the minimum cover. So this is the example 1. This is the essential prime implicant. This is the minimum cover. Example 2. Now this is example 2. Can you see here? We do this, we do this, we do this, and we do this. Okay, now it's a very tricky thingy. It's a very tricky thingy. Now, please look at here. And this example 2 is a little bit tricky. This is a little tricky. Now, if you look at this expression, is it in a standard sum of the minterm expression? No. Is it a reduced expression? No, it is not a reduced expression. Why it is not a reduced expression? Why? I will explain this. Why not? Now we want to. This is an unreduced SOP expression. It can be further reduced. It can be further reduced. Okay. Now if you look at a standard SOP expression, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many terms? 9 min terms. How many literals? 36. This is 36 literals. Now this is 36 literals. 9 min term. Each min term consists of 4 literals. So this is 36 literals. Okay. Now if you look at this expression, how many literals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got it? Okay. Now we want to populate this value from here to here. Now which are covered by this ABC? These two ones. Why ABC? A is not changing. B is not changing. And C is not changing. Got it? We got this from here to here. Now, this is the green one, this is the red one, and this one is the. Can you see here? Now, the green one and the black one can be combined. This is not reduced expression. This is not a reduced, and we need to further reduce it. How can we further reduce it? So I can give you a SOP expression which is still better than the standard sum of the minterm expression form, but not that much reduced. It is not fully reduced. So now this is an example 2. So in example 2 is given you an example in which we have. Okay. Now please remember how many literals are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We can further reduce it. We take the same example, unreduced SOP expression. This is unreduced SOP expression. Now we take the same example. We take this, and we take this. How many literals? 6. Can you see here? Now we combine this. We combine these two, and then we combine all the 4 corners. Okay. In the original expression, how many literals? 11. And this one? 6. All ones are covered or not? Yes. When all ones are covered, is anyone redundant? No. Nothing is redundant. We can proceed further. So now we have an unreduced SOP expression with 11 literals, and then we have reduced it to the reduced SOP expression with how many? 6 literals. So this is an example. So I may also give you a SOP expression which is reduced compared to the standard sum of the minterm expression form, and then you need to further reduce it. This is also another. This example 2 is that example. Got it? So please go through all these examples, and please think that now. Please. When I assume that if you are practicing at home, what you should do? This is your question. I want to further reduce it, and what is your answer? This is your answer. Got it? Now we do another example. Example number 3. Now in example number 3, if you look at here, so now in example number 3, we have this sigma of m. What expression is this? Yes. What is this form? Sum of the minterm form. 2, 8, 10, and 15. How many ones? 4 ones. 1, 2, 3, 4. Okay. 2. Where is 2? What is the code for 2? 0, 0, 1, 0. 0, 0, 1, 0. 0, 0, 1, 0. No. 0, 0, 1, 0. Got it? How do you do it? I have no problem. I did the animation thing. This belongs to this. This 8 belongs to this. This 10 belongs to here. And 15 belongs to here. Got it? Now we have this is the sum of the minterm form. We fill all of the entries. And then D, don't care. What are the don't care? Any or color coding. Please go through this color coding. Okay, do we need to have an additional term A bar, B bar? Can you see here? We can come because now if we don't have this don't care, it would have been a problem. Now we have don't care, we can have a big group. Yes, please. Which one? 0, 1. It depends on 0. 0 means A0, B0, C0, D0. This one. 1. This one. Yellow one. Because 0, 0, 0, 1. What is the MSB? A. A is the MSB. When A is the MSB, so now we said straightforward 0, 0, 0, 1. So this is 0, 0, 0, 1. If we put AB here and CD here, this will change. Got it or not got it? This is the only thing that now if we put AB instead of the in this order, so if we swap, if we put AB here and CD here, all the values will change. Now you got it? Good. Now, so we get the bigger term, and now we can combine these two. And if you look at here, how many literals? How many literals? 5 literals. And without don't care? More or less? Just a guess. More. Why more? Because this X is combined in the bigger group. And in the absence, then we have more. Yes, please. Which one? No. Because if we are not interested in X, but that redundant, then it's become redundant.
Why? Because there is one X.
No, you don't need to cover X. You are not interested in don't care. We are only interested in what? 1. We are interested in 1. We are not interested in X.
Why? Because
we group X with the 1. Yes, we group X with the 1 in order to minimize our expression. But X is not important for us. X is just like a supporting element. It's not the prime element. Got it? So that's the thing. So X is not the essential thingy. X is a redundant thingy. Why you want to add it redundant? It can supplement it. It can supplement the expression, but it is not the primary. Got it? Any question? Should we proceed? Should we? Yes, please. Here it's given. Yes, if I say sigma D 5, 9, 13, so I put in the corresponding. It will given. It will, but it also depends on the problem statement. If I say BCD, then 10 to 15. So you need to know the problem scenario. So it varies from scenario to scenario. Got it? So if we say it's from scenario to scenario, so it depends on the scenario, and then we can say where to put X and how to put X. Okay, now to find the simplest past expression for example number 2. So find the past expression for example number. Now we have example number 2. We did the example number 2. Draw the comma of F, F, and F bar. Now this is F or F bar? F or F bar? F. Then we need, if we want to get F bar, what do we do? In what? Okay. Then we can say from KMF of F, now we get F bar. This is what? A group of 4. This is A bar B. So A bar D to BC bar D. I'm not going to explain it now further because this is too simple. So how then we want to get the past expression. What should we do? In what? In what? So using De Morgan theorem, we apply De Morgan theorem. This is A plus B bar, and then we can directly. So now this is the De Morgan theorem. We replace dot with plus, replace plus with complement the literal and blah blah. Any question? Should we proceed? So this is also how it works. Now this is example number 4. Now example number 5. I'm doing a lot of examples. I'm giving a lot of examples for the sake, so you should go do this. Okay. Now what is this? KMF of what? F. What is this? KMF of F bar. And then from F bar, we have this example. Then we do this, and then this. Any question? Should we proceed? Now this is how do we do some function. Now, but sometime it's very important. Sometime some logical description will be given to us. Some logical description will be given, and we can derive some truth table from that logical expression. Assume. Now I will give you some problem, and then stopping it, and then it's a task for you. Please, everyone.